So in this session, I'm going to tell you about two things. The second thing is a proposal that I'm making to improve Python into the future. It is PEP 551 on bringing security transparency to Python. The first thing I'm going to tell you about is why that's important and why you need it. And the reason you need it is, so I did some research. Before this talk, I did my research, I went into your company, and I had a look at your network security. And you should recognize this because this is your network security. Everything in here are the bad guys. And this little section down here are the ones who are successful. Who here has ever received a spam email with an attachment? Those are all the guys in the top. Who here has, I'm sure no one here has, who here has a colleague who has opened one of those attachments? All right, now those are the guys at the bottom. But being a successful bad guy doesn't actually mean that you've lost. And so in the rest of this, I'm going to go through why that's a big deal, how we can deal with it, and how my proposal is going to help Python help you deal with it. So first, let's take a look at some of the vulnerabilities that you are going to be facing. This is an example of exploiting a buffer overflow in an old version of Python. This has been fixed, so if you're up to date, then it's not going to work. But I want to show an actual example, because a lot of people haven't seen what exploiting a buffer overflow looks like, even though we know that they're really bad security vulnerabilities. In this case, this is the content of a packet that you can send to a Python server, and if it's using the receive from function, that's going to overflow the buffer. Let me take the padding out of this, and you can see there's some hex values in there. Those would actually be encoded. There are addresses of various things. And the padding is there to make sure you overwrite the right parts of the stack. So the stack in C, for those who aren't familiar with it, has more than just local variables. It's got various addresses, pointers. If you overwrite it, you can change what the program is going to do next. You can change the return location from a function. That's what this last value is, the one starting with E. That is the address for this particular target system of the system function. And then the bit that comes after it is the argument we're going to pass to it. We're going to execute bash. This is a proof of concept. You'd more realistically have some sort of command like this, which is going to go off and grab some arbitrary code from the internet and run it with Python on your machine. How do you prevent people getting into your systems through these kind of vulnerabilities? The answer, patch all the things all the time. Many of the recent exploits you've heard, the reason why so many of you have credit freezes right now are because various people did not patch everything all the time. Someone found out that a vulnerability existed and they used it to get into that system. But even if you've patched everything, even if all of your software is as up to date as it possibly can, there is a bigger, scarier class of vulnerabilities than buffer overruns. Pop quiz. Which one of these is fake? Or better yet, which one of these do you not want to actually type your password into? There is a correct answer, and it is possible to tell. Who says the one on the left is fake? Who says the one on the right is fake? The answer is the one on the right. You can tell it's fake because the battery's at 100%. But you can also tell by a few little things there's some interactive methods, so it's not completely foolproof. How many of you have a colleague who would see this pop up and enter their password into it? The entire room. It turns out that even easier than finding a buffer overrun in someone's software and carefully constructing a packet with addresses to functions of the particular version of glibc that's on that machine and filling in the arguments to execute arbitrary code on that machine, it's easier just to ask the user what their password is. And most of them will give it to you. There's a Python hacking tool out there called Bella that will detect iTunes, pause it, pop up a dialog saying you need to enter your password to get iTunes back, and then just saves the password and unpauses iTunes. This is ridiculously successful and very easy. What's the fix for this? Okay, that got about the reaction I expected, because users learn, they're all very interested in sacrificing their ability to get work done in order to protect your network security, make sure that nobody's getting in who shouldn't be, never take work home, never log in with personal device. Yeah, okay, that's not going to work. We could try this. This would work. No more users, no one to give out passwords, no one's getting it. No more work getting done, no more income, no more need for sysadmin. Okay. As soon as people are involved, attackers are going to get in. There's always going to be someone, possibly a recruiter. A recruiter is always going to open an email that says, I really, really, really want to work in some dark office at your bank. .doc. Space, 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 .exe. So your network security is always going to look like this. Which brings in a concept that has been around in network security for a while, but is really solidifying as something that we can talk about. It's called assume breach. And this is a mindset to defending your network that says people are going to get in. The only people who are not going to get into your network are the people who don't care about you. And even then, people still want to get into your computers so they can use them as botnets, distributed denial of service against other people who they do care about, and they just got into yours because it was easy. Assume breach says that people are already in. What do we do now? Let me illustrate this with a few series of animated graphics. We have bad guys in the world somewhere, and they're trying to get to your piggy bank of valuable data. Emails, social security numbers, employee info, whatever that happens to be. Ideally, for them, they're just going to go straight in and take it. That doesn't work because they don't have access because you keep all that stuff private. However, you have computers on your network that do have access to that. And if the attackers can get into that computer, then they can get into the crown jewels. Or you have multiple computers that can get into each other. And if the attackers can get into any one of those computers, they can get from there into the next computer and eventually find one that has access and go get whatever they like. But it gets worse because you've got employees. And so there's devices on your network that you don't think are there. Because someone has brought their phone in, connected to Wi-Fi, and you don't know what else they've brought in. They brought a laptop in, connected to Wi-Fi, you don't know what they've brought. They've got work on it. But it gets even worse. Do you know about every single router on your network? Do you know what versions of firmware it's using? Do you know what vulnerabilities it has? Your attackers do. Do you know about all the network printers on your network? Your attackers do. Every network-connected projector, network-connected coffee machine, light bulb, thermostat. The point of assume breach is that your attackers are far more patient than you and they know your network better than you ever will. I have literally seen maps. The researchers have gone out to network sysadministrators and say, draw me a map of your complete network. And they come back with, 100, 200 computers with lines drawn between them, and it's great. And then they go to the penetration testers who have attacked that network and say, give us your map of this network. And there's 1,000 nodes on it with 10 times as many lines between everything as the sysadmins thought they actually had. You can't control everything on your network. You can't prevent anyone getting in. What do you do next? An attack looks like three parts. First is infiltrate. We just talked about that. They're going to get in. You will do the best you can to protect against attackers getting in. Assume breach says, assume that you will fail eventually. What do you do next? The next thing an attacker is going to do is try to persist. They want to keep code in your network. They want to stay in your network. And so what you do in that case is you want to detect them. Their aim is to get in, hide, and stay there. And these days we're seeing what are called advanced persistent threats, where they stay there for years without taking anything, without causing any damage, just sitting inside your network, replicating from machine to machine, completely undetected, and able to do whatever they want, whenever they want, because they've persisted so well and you haven't detected them. And finally, they're going to try and exfiltrate. They're going to take your data and get it out, again, without you noticing. And people don't notice. Attackers have exfiltrated gigabytes to terabytes of data from companies, and companies don't notice. because they hide it as part of normal traffic. But you have to respond. Once you've detected an attacker in your network, it's track them down, it's shut them down, it's get them out. Persistence is the interesting one, because this is where we want to detect them. When an attacker is looking to persist their malware in your network, they're looking for a range of things that it can do. They really want to execute non-compiled code. This is anything that can be run in memory. This is a state machine that, given some data, they can execute. This is a Python file that they can just exec or eval, execute code. They don't want any validation. Most machines or most operating systems have the ability to whitelist binary code or add extra validation, code signing, to rule out certain pieces of code that aren't trusted from running. Attackers want to avoid that because they can't necessarily sign their code with something that your machine will trust. They want to be able to write files so that they can persist, change settings, access the network to spread from machine to machine, create servers, because when it comes time to interact with it, someone's going to want to log into that machine. And if they can spin up any kind of interactive server, then they want to be able to do that, and they don't want any logging. That's how you get found. Some examples of tools that you're likely to find on your network that can do this. Bash. Pretty good for this. Depends how complex a program you want to write in it. PowerShell is very good, very popular. Except in more recent versions of PowerShell, we've invested heavily in the security, and so this is not such a good option because a lot of the proposal for Python that I'm going to present has already been done for PowerShell. So you can heavily restrict what code it's allowed to run, where it can come from, and log everything so that if PowerShell is used for anything, you know exactly what it was used for. Perl, again, if you really want, and of course the reason we're here talking, Python is an ideal tool. It fits all of these characteristics, and it's by design. Python is designed to do all of these things, which makes it really hard. And so the response from a lot of sysadmins is to simply remove them from the systems. If you go for a minimal server image, you're going to avoid as many of those tools as you possibly can because of the ways they can be misused. Again, this is right up there with ban all your users. It prevents you from actually getting work done. So the middle ground, instead of banning it, is to audit them. It's to know what they're doing, continuously be collecting as much insight as you can into what they're doing, who caused them to do it, what they're accessing, and just know at all times what all of these tools are doing so that you can make the determination, is this a good thing, is this a bad thing? This is security transparency. This is being able to see into your systems, all of your systems, and have a good understanding of whether they are being used for good purposes or evil purposes. So PEP 551 is a proposal to introduce features into Python that will help it be more security transparent. The aim is to take this statement that people have said Python is banned on this network and change it so that they can say Python is okay because it's audited. Because we know what Python is doing, we can tell the difference between when it's doing good and when it's doing bad. We don't have to just outright ban it. As a developer who works in Python, you don't want Python to be banned because you want to be able to write production code in it. You want all the benefits of being able to work in Python, which means you need to get the system administrators on side so they're willing to let you do that and not take a stand in the name of security and say you cannot use Python on these production machines. Who knows what this does? Exactly the number of people who I've shown these slides to before. So this is one line of Python code that is executing arbitrary code. This is the kind of thing that an attacker is going to throw at your Python on your machine to get initial access. This is just a big blob of base64 encoded text. The nice thing about base64 encoding is you can take multiple lines of code and render it as one line of code. We can import base64 and decode it, and then execute and eval it, which lets us do any number of things. And in this case, if we run it, again, Python-C, so I don't have to have a file on the machine. All I need to do is that earlier vulnerability with the buffer overflow to let me run one single command, and I can get completely owned. If you want to try it yourself, all of the code is in that QR code. I didn't expect anyone to take a photo of this slide and copy it out, but feel free. Security transparency and the hooks that PEP 551 proposes are meant to answer these questions. What code is actually running? Because looking at that command line, if that's all you're going to see in your normal log, you have no idea what it's doing. What files or network access occurs? Where is it getting its information from? Where is it putting new information? Where is it storing itself? Where is it replicating to? And what red flags are there? Because a lot of code does this. All of your code is going to access files, access network, and it's going to run a whole lot of code. So you need the red flags to be able to say, this should not be happening. There is something weird going on we need to investigate. This is a sample of the log file that my reference implementation of this PEP comes up with. It's heavily abbreviated. You'll see there's a few lines there that say imports X number of other modules. That one bit of code actually imports over 100 modules. So simply, if you've wondered why Python starts up slowly, it imports a lot of stuff at startup. But simply having a lot of modules being imported doesn't give you any red flags. There are some red flags in here though, because it's very rare that you're going to have deployed production code that's been code reviewed, checked into GitHub, or checked into whatever CI, run through CI, tested, published, or deployed, that is evaluating from a string. Anytime you see compiling a string object, that's probably a red flag. And you'll see in the first case is actually the code that was hidden inside that base64 string. Because whenever we hit an eval or an exec, we've got to go off and compile a string. So in this case, the log has just dropped out exactly what that code is that was hidden behind that big blob of characters. And then the later one down the bottom is a second set of code that's been run. We can see in between network access. There are hooks that take every URL open call, every socket that's created, every address that's resolved, and just dumps it. So all it's doing is just providing the ability to access that information as it happens. In this case, we've put it in a log, but it means we can now see where it's getting its data from. And this is a very important point about this proposal. PEP 551 does not automatically make Python more secure. Because with the reference implementation of this PEP, actually nothing changes in a normal install of Python. What has changed is there are now hooks there. If you're listening to those hooks, you get more information. By default, Python does not listen to those hooks because it can't do anything with the information. It can make a huge, huge, huge log file. But most defenders don't actually want a huge, huge, huge log file because they have a security system. If you're serious enough about defending your system to be interested in this, you already have logging set up because your operating system will log many of these events for other things. Your operating system is going to log every process that gets started. It's going to log potentially files that are accessed in various places or everywhere. It's going to log network connections in certain ways. If you're not paying attention to that, this proposal doesn't help you because you'll continue to not pay attention to the extra information. If it will help you, you have a system to integrate it into, and so that's your responsibility. The API is on either the next slide or 2 slides. But the integrity of your system is your job, or someone you pay to care about making sure that everything interoperates properly. But if you have system deintegration, audit deintegration, if you're using the event log on Windows, ETW tracing, then you will want to take these hooks and add the integration points yourself to make sure that all your events are in the same place. So all the transparency you already have in the operating system, these will let you add Python into that, so you also have insight into Python mixed in with everything else. That amount of information is huge, significant. You need to determine what looks good, what looks bad. But by adding this in, the ability for attackers to hide inside a Python process is gone. And that stream of events from the operating system now includes the events from Python, and you can see into them. So what events are these? What do we hook? And this list is incomplete because it's trivially easy to add more hooks, and the proposal isn't yet merged into Python, so we still have the flexibility to add more things. But here's a brief grouping. There are things that all code does that get logged. Every single import gets notified, gets audited. You can see every single module that gets imported. You can see every bit of code that gets compiled. Every socket created, every access to the network by URL lib, which is the lowest level, so basically everything will go through that at some point. All hooked. You can see all of those. There are things that most code never does. These are also very interesting because your code might do this, but you'll know about it. But if you see them happening, you probably want to take a closer look. Exec, eval, going to show up from time to time. ID is, if you're interested in why ID is a big deal, then come chat to me afterwards. And I'll introduce you to someone who exploited that to make tuples mutable. Array in C types, struct, which lets you redefine how plain old memory looks and interpret it into Python. It's rare but very useful for certain attacks. There's a whole range of functions in the sys module that let you change the state of things, adding traces, adding debuggers, adding profiling. You're very rarely going to do it. You want to know if someone does, because you don't know what they're doing with it. And also monkey patching. If you've ever wanted to see every bit of monkey patching that happens in your code, there is a hook here that will let you audit that and see every time someone changes an attribute on a class. And finally, there's events that no one should ever do. For example, if you've set up an audit hook so that you have some code to be called whenever an event happens, if someone else does that, they probably shouldn't be doing that because you did that. So you get to hear about it. Code type new, function type, this is directly instantiating a code object, which again, very useful if you want to exploit Python. Very, very, very rare in genuinely good code, and if it gets through a code review, then you've got a hard discussion to have with the code reviewer. Sys.getFrame or current frames. Again, I'll take a stand on sys.getFrame. Don't do that. But again, people do. And unpickler.findClass. If you've ever been told don't use pickle because it's not safe, it's because of this function, you will now get called via a PET551 audit hook, so you can do whatever you want. You can raise a big red flag, or you can just crash. So the API for this, there's two APIs. There's a C API and a Python API. Again, if you care enough to be doing this, then I'm going to assume that you care enough to compile a new entry point. If this is merged into Python, you don't have to recompile the whole thing. But the entry point, which is typically one line of code, can have a second line of code that sets up an audit hook. Then when you initialize Python, every single thing that it does is going to go to your C function. It's going to go to the C function first. It's the most secure way of doing this. It's not possible to remove from within Python. And that's this. The API is very straightforward. You get the name of the event that's coming in, and you get a tuple of values. The schema for those is matched to the event name. Those are all defined in the PEP, and those will not change over time. So if you receive the import event, you know what the arguments are. You can parse them. You can do whatever you choose with them. They aren't going to change. There's also a Python API for this, so that if you want to quickly write a hook or something that you don't mind not starting until the process is running and potentially already compromised, then you can add it later on. And this is handy for testing, it's handy for debugging, and it's handy if you simply want to do things like detect all monkey patching that happens while you're running your tests. Then it's perfectly fine to use these hooks from the Python API during something like running tests. And a neat thing here is you don't have to succeed these. If you raise an exception from any of these hooks, it's going to bubble out, and it's probably going to bring the process down. So if there are things that you know about that should never happen, you can crash, essentially, in these hooks. As an example, one of the exploits that I've seen generates an invalid code object that is then used to modify values that it shouldn't have access to. In the hook for creating a new code object, I added a few lines of code to validate the code object, just scan the bytecode it was passing in, and if it's invalid, it raises an exception, and now that exploit is broken because you can't create a callable code object from compromised code. So it's very handy for this. Again, the main point of these enhancements is transparency, not protection. Getting a log message is far more important than stopping the process. Here's an example of this with a few bits in it. From that bit of code earlier, we saw in the log that it was going through a bit.ly URL to get to its payload. We don't use bit.ly in our app. We know that. None of our URLs use bit.ly. No user-provided data should ever be doing that. So we're happy to say if someone is trying to go through a bit.ly URL, we'll just block it. We'll just cancel it. So here are the pieces of this. This hook gets called with the event name. Every time we create the request object, it's going to be passed in some arguments. The first of these is the URL. So we can look for some pattern in this. You could use a regex instead. You could use any sort of matching you like here. We're going to display a message. We're going to log and detect and report that this is going on. And for good measure here, we're actually just going to abort it. And so someone who thinks they're constructing a request object or they're calling URL open is going to see an error they don't expect. Chances are it's going to bring down the whole process. You could catch this and do something different. And if you really want to prevent that, then you do something like os.exit that is uncatchable. And finally, we're just going to use a Python API to add this hook, which does mean that if someone has something run before we add this hook, then it's going to get through and we're not going to know about it. Again, depending on your purposes, that may not be a big deal. So with this hook, if I take this code and run it again, we get different output. You'll see that we get the warning first, and then we bring down the whole process with an error message, rather than letting it even occur. To sum up where this proposal is at, as I say, it's a proposal. PEP 551, it's published online, you can look it up and find it for all the details, but it's not in CPython yet. Still working through the proposal process to get it in. There is a working implementation. I have published that. It's on my GitHub, linked below from the tiny URL, either against Python 3.7.0 Alpha 2, which is the latest version of 3.7, and also against Python 3.6.3. Works on Windows, Mac, Linux. It's completely cross-platform because it doesn't really do anything yet until you add your half of the implementation to integrate into your auditing system. My contact is there if you want to get in touch with me, or you can get in touch with me on Twitter. Happy to take any questions about this, and would certainly love to hear your feedback, and if your organization or company is interested in making use of it. Thank you. Yes. Performance penalty. So, in the benchmarks that I have run, and I have run benchmarks, if you don't add any audit hooks at all, there is no performance penalty. And I say that based, I know, with a room full of data people, no one's going to believe that. But the benchmark suite has been fairly well validated at this point. Some benchmarks came in faster, some came in slower. There's no good reason for them to be faster, but none of them had a statistically significant difference. Everywhere there is a hook is already a slow operation. So if you're downloading something off the network, then checking to see whether you should call an auditing hook is very cheap compared to waiting for the internet to get back to you. And that's the case for essentially all of these calls. Possibly ID is the only slow one. Again, shouldn't really be using ID. And to be clear, hash does not go through the ID function. So that's not going to affect hashing or dictionary lookups or anything like that. So performance-wise, no impact when you're not using it. If you are using it, then you get to control it. You get to decide what the performance impact will be based on how well you optimize your audit hook. If you write it in C and you have efficient string comparisons for the event name, which comes in as a plain old string, it can be as fast as you like it to be. And most auditing or logging platforms, especially for security or OS level stuff, are already highly optimized. So you're unlikely to have a huge impact, but it depends on how much you're logging and what you're doing with it. But it is entirely up to you if you do use it.
So this idea is really exciting, and I personally cannot wait for security focused organizations are implementing it. So I have a question about the slide. you mentioned in the second column that C type is a very dangerous module that not a lot of code uses. But what about NumPy and PyData, which are just as, if not more dangerous than C type, and yet incredibly common, and nobody built NumPy for source, and nobody can build PyData for source. So we can't add single line.
No, that's certainly the case. And NumPy has plenty of Python level places where you could add hooks. There is an API that I didn't mention to actually audit something. So if you want to add an auditing event to, say, a third-party library, if this is accepted, then as of a certain version, there would be a sys.audit function that is always there. It's not conditional. You don't have to check for it. It's very cheap to call if there's no hook enabled. But it is there. It is callable, and that can let you add new auditing events to other libraries. If you want to hear from, say, NumPy or PyWin32 what it's doing, there's a C-level equivalent. But as you say, there are dangerous libraries. C-types is in the standard library. If someone's using that, they could be doing all sorts of stuff, and it's very interesting to know what that is, even if your own code is using it. And PyWin32 is much the same for Windows. I would strongly recommend trying to avoid that if possible. If only because if you start reading books that people have written about hacking Windows using Python, page 1 is essentially install PyWin32. And then the rest of the book assumes you have PyWin32. So if you can find a way, either by figuring out what APIs you need to call and setting up your own Siphon module, or even like a precompiled CFFI module to call those so you don't have to use dynamic lookups on the machine, then that's going to be a big advantage. And avoiding the well-known big modules like PyWin32, I'm not saying avoid NumPy. NumPy has certainly had buffer overflow issues. And if you find those, then you need to report and patch them. But the advantage that PEP 551 brings in that case is you still have to do something with the buffer overflow. And if that involves running more Python code, this proposal will help you see that and give you enough information to trace back and find that it was a buffer overflow in NumPy that was exploited to get you there. You may not have that amount of information without the transparency that comes through having this in Python. Yes? So in the case where you have a library that you've written in C, if you've written it yourself, then you obviously have the freedom to add your own auditing hooks directly. If it's like an in-house proprietary library, there is, as I said, there's a C API for adding hooks that becomes available with the patch, or if this gets merged into Python, it will be there and let you have sort of formal hooks added to your own code. Or alternatively, if you hook at the outside, again, the value here is determining if someone is trying to exploit Python on your machine or trying to hide their activity. And if your library is not helpful for that, then it's likely not going to be helpful to an attacker, and logging it may just be adding noise to the logs without adding anything useful. It's really an evaluation that you have to make for yourself based on the purpose and the use of the library. Yes? Yeah, so the question is there any way to avoid event names colliding? No. And that may be something that's worth adding into the PEP as a recommendation for third parties. I would say prefix your event names with your package name. And then at the very least, people can't have two colliding packages installed at the same time, because if you have numpy.events because you've got numpy, someone else should not have those events. But again, even when you deploy this, one of the first things you need to do is look at the events and see that you're getting useful information. And that should show you fairly quickly if you have colliding names for events, because you're going to see all sorts of issues. If there's no other questions, thank you very much. I'll be around today. Feel free to come up and chat.